Dear students, in today's class, we take the example of two-component system involving formation of compound with congruent melting point. In the previous class, we have seen the general phase diagram of such a system. We have two examples to discuss. The first one is Zinc-Magnesium system. This is one which we discussed in today's class. Zinc-Magnesium system is an intermetallic system, two metals which can form an intermetallic compound. So the compound formed here is di-zinc-magnesium, or you can call it magnesium zincite. The stoichiometry is Mg plus 2Zn giving MgZn twice. So magnesium and zinc enter into chemical combination forming a distinct compound. And also the compound formed melt congruently. It's a stable compound. That means it melts into the liquid form at a constant temperature such that the solid and liquid phase have the same composition. They exist in equilibrium. Let's see the phase diagram. Similar to the general phase diagram, it has the same shape. The points are A, B, C, D and E. What is point A? You know, temperature is plotted against composition. Here it is 100% zinc, so 0% what? Magnesium. It is understood. This can also be expressed in terms of mole fraction. Some people follow that. And 100% magnesium and 0% zinc. So the point A indicate the melting point or freezing point of zinc, which is 420 degrees Celsius. Point B represent, it is the melting point of magnesium. Of course, it has higher melting point, a little harder metal, that is 650 degrees Celsius. And point D is represent the compound formation, right? And you know, MgZn twice definitely indicate the stoichiometry where it is 2/3 zinc. So it is 66.67% zinc. Naturally, 33.33% will be magnesium. Okay, so this is the composition at which the compound is formed. So this point D is for the melting point or freezing point of this compound di-zinc magnesium, which is 590 degrees Celsius. See that here this melting point is in between that of zinc as well as magnesium. It can vary, I have told in the previous class. It can be above or below or in between. Fine. Now coming to the curves, this is one curve AC. This is BE and CDE. We have to explain various aspects of this phase diagram. See the area here, when we consider the area here consists of only liquid melt of magnesium and zinc of various composition. We know the phase rule which we apply is always reduced phase rule or condensed phase rule, which because we neglect the vapor phase here, so it is +1. And in this area you have only one phase, so it's a two-component system. Applying this, you get 2 minus 1 plus 1 equal 2. So F equal 2 in this area system is bivariant. Now point A is the melting point or freezing point of zinc. What will be in equilibrium there? Zinc solid in equilibrium with zinc liquid, right? That is the melting point of zinc. Applying phase rule here, you know, it will be 2 minus, it's not 2, it's 1, because I have told you the 2 points A and B which represent 100% zinc or magnesium reduces to a one component system. So it is 1 minus, and two phases in equilibrium, 2 plus 1 equals 0. So practically this point A and point B are invariant. Okay, because pressure is kept constant, so a constant pressure will correspond to one and only melting point. Melting point will be also constant, right? That's why. So point A, melting point of zinc. Point B also is invariant, melting point of magnesium, where solid magnesium will be in equilibrium with liquid magnesium. Right. Now coming to the curves. Similarly, one more point. Point D. Point D is the congruent melting point of the compound di-zinc-magnesium, where the solid and liquid form of the two with the same composition will be in equilibrium. So here also F equal, it is again a very important point. This point D also reduces to a one component system, because here only the compound exists. Only one component, the compound exists. So it is 1 minus 2 plus 1 equal, it is also 0, invariant. So this point is also invariant. Point A, point B and point D are all invariant because they represent the melting point of the pure component. Here it is zinc, here it is magnesium, and here it is the compound. See, this diagram can be seen to be, or it can be thought to have combined of two simple utility system. I have told you this feature. Either utility സിസ്റ്റത്തിന്റെ ഫേസ് ഡയഗ്രാം, ഇത് മറ്റൊരു യൂട്ടിലിറ്റി സിസ്റ്റം, രണ്ടും കൂടെ ഇവിടെ ജോയിൻ ചെയ്ത പോലെ കണക്കാക്കാം. അപ്പൊ ഹിയർ ഇറ്റ് ഇസ് എ സിസ്റ്റം ബിറ്റ്വീൻ zinc and MgZn twice. This is the system between MgZn twice and magnesium. Okay, now this area is bivariant. Coming to the curves. In the curves, let us take curve AC. What is this curve AC representing? What is this called? This is the melting point of zinc, and when you move in this direction, you are adding increasing amount of magnesium. So this represents decreasing melting point of zinc on adding increasing amount of magnesium. So we call this curve AC as melting point or freezing point curve of which one? Freezing point curve of zinc, right? How the freezing point or melting point of zinc decreases on adding magnesium. What about BE? Curve BE represent, it is the freezing point curve of magnesium. That means how the melting point or freezing point of magnesium decreases on adding increasing amount of zinc. Now what about the curve CDE, which has two parts? What is DC representing? Altogether, CD can be called the freezing point curve of the compound MgZn twice, in which DC represent the decreasing melting point or freezing point of the compound MgZn twice on adding increasing amount of zinc, and DE represent decreasing melting point or freezing point of the compound MgZn twice on adding increasing amount of magnesium, right? Now along all these curves, what is the variance? That's the question. Along all these curves, what is the variance? You can easily see the phases in equilibrium. See, along this curve, what is in equilibrium? It will be seen here. Here it will be zinc and the liquid melt will be in equilibrium. See, when you cool this mixture, the liquid melt of this composition, when you cool, what happens? When the temperature touches the curve, the solid zinc starts coming out. So solid zinc in equilibrium with the remaining liquid melt. Two phases in equilibrium. Here it is magnesium in equilibrium with the liquid melt of varying composition. And here, along this curve, it is MgZn twice solid in equilibrium with the liquid melt of varying composition. So two phases are in equilibrium here. So F equal, two component system, it is 2 minus 2 plus 1 equal, it is 1. System is monovariant along all the curves. That's a common feature in any phase diagram. System is monovariant, right? Now finally, coming to eutectic points. There are two eutectic points. When we consider the points, we already spoke about point A, point B and point C, which are all invariant. Now it is a triple points, that is what is more important. There are 2 points C and E. What about C? What are in equilibrium? Here, solid zinc, solid compound MgZn twice, and the liquid will be in equilibrium. Or you can say solid zinc, eutectic mixture and liquid. See, eutectic mixture will contain both zinc and the compound. So basically zinc is already there. So in short we can say three phases in equilibrium at point C are solid zinc in equilibrium with the compound MgZn twice, in equilibrium with the liquid melt. Three phases in equilibrium. What about point E? At point E, it will be solid magnesium, then the compound and the liquid. Instead of zinc, it will be magnesium. Everything else remains same. Applying phase rule at these eutectic points. F equal 3 phases in equilibrium. So 2 components minus 3 phases plus 1 equals 0. System is invariant at these 2 points. That means these are fixed. See, here you can see the temperature is 380 degree. That is the eutectic temperature for this point, and this here it is 347 degrees Celsius. So these are the eutectic points. What about this area? Here it is solid zinc and eutectic mixture will be in equilibrium. Here it is solid magnesium and the eutectic mixture or the compound will be in equilibrium. Finally, the cooling of various liquid melt. What happens? Let's take various cooling. Okay, suppose you take this composition of zinc and magnesium, say 90% zinc and 10% magnesium, you heat it strongly, melt it, you have a liquid solution of zinc and magnesium. One phase, you are here bivariant. Cool it. When you come down, suppose this is A, this is B. When it is B, the temperature reaches B, what happens? Solid zinc comes out, starts coming out. So that the composition of the remaining liquid will be more in magnesium. Composition of magnesium increases in the remaining liquid. Of course, you will move along this curve. Or when your temperature falls, more and more zinc separates out, and when the temperature reaches this point, that is eutectic temperature, what happens? Eutectic mixture starts coming out. That means both zinc and the compound together comes out as a eutectic mixture. Temperature then remain constant, that is eutectic halt, until the whole liquid melt solidifies into the solid form of zinc and MgZn twice. Okay, when the liquid phase disappears, again the system becomes monovariant. When there will be only solid zinc and MgZn twice, which further cools down. That is, the graph will go down after the solidification is over. What about cooling heat? This composition. You take the liquid melt of this composition. What happens when you cool it? When the temperature touches here, the curve, which solid will comes out? This area is that of the compound, MgZn twice. So solid MgZn twice will separate out, composition will move along this curve, and when temperature reaches C, that is eutectic temperature, eutectic mixture of zinc as well as the compound will come out until the whole liquid is solidified. Cooling this part, you will be getting again when you take this composition and melt it and cool. When the temperature touches, when temperature reaches this point, which will come out again, this is the area of the compound, solid MgZn twice will come out. The composition of the remaining liquid will move along this, and when temperature reaches this eutectic temperature, both compound MgZn twice and the magnesium solid will start separating out. until solidification is over. Finally, again, when you take this composition, what happens? This, if you cool the liquid melt of this composition, when the temperature touches the curve, solid magnesium starts coming out, and the composition move along this direction, and at E, eutectic mixture starts coming out. Finally, what about cooling this particular composition? What is this? This is the composition corresponding to 66.67% zinc and 33.33% magnesium, which correspond to the stoichiometry of the compound. This composition mixture melt cool. When you cool it, when temperature touches this, what is this? This is the congruent melting point of this compound. This temperature, a liquid and the complete compound. Neither zinc nor magnesium alone comes out. Only the compound comes out. Now, equilibrium, see, this compound separate here two composition solid MgZn twice, liquid magnesium zinc ratio right? So this is absolutely the melting point or freezing point of the compound. Okay, that's why we call it congruent melting point. But here complete solidification compound form because our correct composition mix nothing is excess. The composition is just up to the formation of the compound. So only the compound will solidify. Other than the composition is solid melt if you you cool it and the whole liquid has solidified into MgZn twice, fine, you got the solid. In pinning cool compound cool and temperature solid chudakiyalo ee chudakiyal MgZn twice ennulla compound chudakiyal adinte temperature tirichu videttumbo adu melt cheyum sadharana oru compound pole. It will melt into the liquid having the same composition. That's why we call it compound with congruent melting point, or it's a stable compound. This is zinc-magnesium system. Okay, we will discuss one more example of this kind of system in the next class. So by discussing these examples, you will understand the various aspects of these kinds of system clearly. Okay, see you in the next class. Thank you.